So here we're talking about the potential energy and equilibrium for a continuum body for an axially loaded elastic bar. And so you can see the picture here. We have a constraint here, and what we're doing is we're pulling on this bar on the end, x equals L with F. Notice that this bar does not have a uniform cross section. It can change as x grows. So we can start off, what's interesting here is you notice that these variables are all functions of x. We start off by describing our axial strain. And if you remember, the strain was equal to du dx. Hopefully you're familiar with that. We are just right now focusing on this continuum body kind of 1D. So we're developing this framework for 1D, and then we'll later extend it to other dimensions. Using the definition of strain, we're able to go ahead and take our stress. Stress is equal to Young's modulus times the strain. Take this definition we have for strain, substitute it in, so we have E du dx. And then we can extend that one more time when we write the strain energy per unit volume of the bar. So our strain energy, we said, was U. We're looking at an increment of U here, which is the area under the stress strain curve, 1/2 sigma times epsilon, which when we substitute our stress in here, we can write the strain energy in terms of du dx. This becomes important in the next step when we start to solve the equations. We're trying to get everything in terms of U, because that's what we ultimately want to get out of the solver, finite element solver, which then we can use our constitutive model, or we can get strain, then we can use our constitutive model to get stress. So U is what we're after right now. And then here we extend that, instead of a per unit volume, we extend it of the entire bar by introducing integral over all those increments of strain energy. So we substitute that in, we go for the integral from x equals 0 to L, and we can make a further substitution on the volume since we're in this is a little weird thing. We're looking at 1D, so we're dx, but we do carry along a cross-sectional area. This is important in our development of, really what we're after is a development of a truss element in finite elements. So trusses can have different thicknesses, and we just bring it in different widths or cross-sectional areas, and we bring it into this area term. So that's kind of can be a little confusing. We're working in 1D, but we also have an area term, cross-section associated with the continuum body we're looking at. So our strain energy is there. We can then write our potential energy. So we have the integral from 0 to L of those body forces times a displacement, let's say at different locations. Those might be nodes described by the mesh that we develop along X. And then the force applied, notice we don't have an integral here. Force times displacement at x equals L, so at the end where we're applying the force. Note that we dropped the minus sign off. We had the minus sign before as like the work done by external loading. However, we do pop it back in down here when we write the total potential energy of the axially loaded bar is given there with the minus signs. So now we have the potential energy of this bar, and what we want to do is say, all right, well, let's say we switch U and we put in W. So W is what we call admissible displacement. We know that it's going to be hard to solve for the exact solution, right? I mean, we're after that. But when we solve this potential energy problem, we're actually going to have some other solution that's going to be W, and it's going to be approximation. We're not going to be able to get the right answer. I mean, very few cases you can do that. And so we have some other displacement that we would have, and it would be admissible. What does this term admissible mean? Well, here's a little schematic of it. This is some solution over the bar. And so the exact solution, let's say, is this solid black line. And then an admissible displacement would be a couple constraints on that. One is that it satisfies the boundary condition. So, for example, we know what the solution is at x equals 0 because it's constrained. So those two solutions are the same here. At the other side, there's a little bit of discrepancy, right? And because here we're applying a force, so the known boundary condition is not known. And so we allow error at that spot. And actually along here, you can see that there's just approximation to the exact solution. It's not the exact result. The other constraint besides the boundary conditions we have to have are that the derivatives don't sort of go to infinity or what we call blow up. So they have to be well behaved too. But this total potential energy can be used for finding an approximate solution W, and that's what we're going to do. One of the techniques we use to get there is something called the Riley-Ritz method. And the Ritz method involves the construction of an assumed displacement field, admissible in some case. So, for example, we have X, Y, and Z displacements, and what we do is we write those in terms of these polynomial functions we construct. So we have, for example, A and phi. And phi here is usually taken as a polynomial. So for example, you can have A1 plus A2x plus A3x squared, where here phi1 here would be 1 over here. We have phi2, so we have a plus sign, right? A plus sign here because of the summation sign. Phi2 is x, and that's here. And then phi3, x squared would be here. All right, and you do that for each one of these displacements that you have. And the only constraint that we have on these things is that they must be kinematically admissible, meaning that boundary conditions are agree with the specified boundary conditions, and they don't blow up. So, for example, let's say u at x equals 0. Well, x would be equal to 0 here, which implies that a1 is equal to 0. So then you use those boundary conditions to basically solve for these unknown coefficients, a, right? And that's kind of how you do that. You can combine it with our previous potential energy. So we can write this whole equation in terms of u, because remember epsilon was du dx squared. So we have everything in terms of u here. And if we take u, which is comprised now of a phi, right, then our potential energy can actually be written in terms of a and these polynomial functions, let's say an x squared, so forth. And so the only unknown there would be these a terms. So we have a number of independent unknowns, and then we can take the minimum, partial of phi with respect to partial of a naught. So this is kind of very similar to what we did in our spring example, although this is a little bit more general now. And you set all those equal to 0, and you solve, and you get a system of equations back that you can actually solve for the a naughts, and then you are able to plug those a naughts back into your polynomial functions you created over here, right? So then you would have an approximate solution for if you plug in an x, for example, and you know these a naughts now, what is u? So that's kind of a neat little idea. This Riley-Ritz method was developed in sort of the mathematics field, which is interesting because you had all these different math tricks that we're going to be relying on in this class, then were combined with computer science as that grew, and it kind of made this modern computational finite element method that we use today. So the history of all this is really interesting. All right, so that wraps it up for today's lecture. The next one that we're going to do involves an application on the pin and lug problem. So we'll do that next time.